Okay, hello everyone. I'm going to go through, like Steve said, the third or fourth of the sessions here, speaking in particular to water budgeting and time series analysis and the tools we have on our website. Just to begin with this, hold on a sec, there we go. I just want to sort of go through what this presentation is not. This is not a presentation for hydrologists, nor is it a presentation for hydrogeologists. And I mean that to say, I don't want to get anyone who's here for a hydrology or hydrogeology presentation to think, oh, this isn't for me. I am a hydrologist, but I'm not concerned about events. Rather, I try to understand system trends at large scales. In that I don't have the liberty to ignore the groundwater system as a hydrologist. And here we're going to talk about a lot of tools that we've put out on the internet. Our colleague Rick likes to call this putting our brains on the internet. And really we are just arming ourselves to answer common questions. So we're looking to gain insight on the hydrological system through an analysis of the drivers of the hydrogeologic system. And that is hydrology. And this presentation follows quite well from the previous two sessions that we've had. In the first one, Steve presented this decision-making idea of the foundation of data-driven decision-making is dependent on the data and the interpretation that and the analysis that we have in stock. And so this is our jurisdiction. This is a perspective of our database, let's call it. We have 13 partners. You could see all the logos of those partners on the sides there. But this area also includes 3 source protection regions, the Credit Valley, Toronto region, and the Central Lake Ontario region, the Trent Conservation Coalition region, and the South Georgian Bay Lake Simcoe region. In the second talk that Rick came, he also presented the same sort of decision-making idea, but revealed that the path to the database decision-making is not linear. Rather, in practice, it's a continual practice of investigation, knowledge capture, reflection that refines our conceptual understanding. Specifically, he spoke to the interpretation element of our program. And I'm going to move to sort of that next echelon in this pyramid and talk about the analysis and the predictive tools, and this will complete our foundation. So this is the third one, and what I really want to do is just to be speaking to that final leap to that golden echelon you see at the top here, at this decision-making part here, and that is data-driven decision-making as idealized in this pyramid analogy. But there are challenges. Having raw data and information derived from the collective professional field, like our partners, doesn't lead to decision-making directly, but indirectly through a set of workflows. Simply having the data isn't enough. It's incomplete. Let me show you what I mean. So to make this leap, we need a workflow. And this workflow, here's a simple iconographic idea of a typical workflow, and I'll just step through these at first. So first there is the database, and we know that database as the foundation to our analysis, to this workflow. And we've already seen what the database is. Here's a perspective of it that shows streamflow stations, climate stations, and boreholes. But of course we're missing other aspects to our database, like the report library, like water quality, like our knowledge capture, like spot flows, and I can go on. That next level, and this is what Rick really touched up on, is the interpretation. How do those data give us a picture of the hydrogeologic, hydrostratigraphic setting that lies beneath our feet? And this has been a culmination in efforts by both public and private agencies that have helped build this, our database and our foundation. The last sort of bit of this echelon is the analysis, and one aspect to this is the model custodianship program that we have, and this is where we hold up to 100 regional scale models of different makes and shapes and sizes. It could be mod flow, fee flow, Mike Shee, HSPF, hydrogeosphere, PRMS, and I can go on. And right now we have a custodianship program where all of these are packaged. They are all operational and they can all be readily shared for those clients or those agencies that would like to use them. So armed with all this, we now have the step of querying the data. And so this is the next step of the workflow. And from those foundational data, one needs to develop this query to obtain the necessary information. And of course, the next step of once you've queried the data is reformatting the data to your favorite platforms that you like to look and analyze the data. Once you've reformatted and imported into something you like to work with, then there's the quality control, and a simple quality control could just be inspection, looking at the data itself. Are there any spurious data points that you may want to remove or adjust or fix or what have you? And then the fun part is the analysis. So once we have everything set, we start to do the analysis, and this could be in terms of some sort of statistical interpretation. This could be some sort of spatial interpolation, and in a related sense, there could be modeling, and this can help with our insight. And I just want to step aside. I want to explain that to us, modeling isn't the end product. We don't collect data to serve models. Rather, we see models as a powerful tool that helps us get further insight into our system. All the while, these models are constrained by what we know, data. And so to us, models are underutilized this way, maybe because they appear too, I don't know, esoteric for decision makers. They just seem out of reach. And here, what we're doing is we're attempting to give non-modelers access to this form of modeling through our web platform. So to talk about the challenge of disparate data, here's a zoom-in picture of our database. And you can see there are climate stations out here, there are monitoring wells down here, and there are streamflow stations out here. But I may want to know, is there a water level response to climate events, such as rainfall or snowmelt or drought, shown in our monitoring wells? If so, how delayed is this response? I may want to know, is there a relationship between base flow regime and groundwater levels? Or I may want to know, how is changing climate affecting the streamflow regime? And sometimes this actually requires modeling. For instance, to obtain snowmelt, which is rarely, if at all, measured, or to relate basin-wide weather forcings to a gauge streamflow outlet, and that's just your classic hydrological model. A couple sessions ago, I know a question I answered was regarding, why are there so many inactive stations? And here's just a little picture I like to put up once in a while. And this is just a survey of the historical climate stations within our jurisdiction. So I've made this into a Gantt chart where I have the oldest installations to the newest at the top to the newest installations at the bottom. And you can see right around the 40s and 50s and 60s, many stations were installed, which were just, which culminated into our highest density of stations in the 1970s. And since a lot of these stations have gone offline and a lot of them haven't been replaced, we are back down to levels we haven't seen since the 30s and 40s. And so be it. How are we going to work with this data? A way to help with this data is that we also have a lot of sites that are at the same location measuring the same thing, but they are termed by different stations, different locations. And so here, for example, this Pefferlaw Brook near Eudora, there are two stations that don't overlap, but when you stick them side by side, it becomes a continuous data set. So working with the data here to extend the data set so we can get a better picture of historical phenomenon and our system's response is what's key here. So going back to our workflow, once we have all that analysis, and then we start looking at presentation, we start putting that analysis in the form of plots, tables, and or maps. And of course, that gets printed and reported and put into presentations. And so this whole workflow is what is necessary to go from the data to the decision making. And that is the challenge. And that's why I say just having the data isn't enough. When you want to actually make decisions or gain insight from the data that we are holding, this workflow has to be done. And this brings me back to the purpose of this presentation, which is to demonstrate some of the many workflows that we've included on our web platform, such that this repetitive process doesn't have to be repeated over and over again. And so I'm going to move on to the website here. That's just a short introduction. And our website we've been working on for a couple of years. We've all sort of put in our bits and efforts, but it's all coming together and painting a really good picture of our system and our systems program. And this website has a lot of resources. You saw the numerical models, you saw the database and the analysis, and some of the analysis I'll show later on. There's a lot of GIS layer information that goes into this. And we're also leveraging a lot of open source tools that have proliferated in the last decade. And through this web platform, we are able to make this available to decision makers. Simply put, these are the tools that we use day to day. Again, I'm not trying to design a product to be marketed or what have you. These are the workflows that Rick, Steve, Mike, Britt, and I have used in-house that we've just put on the website to make our lives easier. The only difference here is that we are willing to share, and we're opening it up to our partners and to the community who want to use our website. So in terms of the website, first I'm really going to talk about the water budget tools, which I must note is still in development. The impetus for this tool was to aid our partners involved in development reviews. That is to confirm water balance calculations presented in development applications. I won't spend too much time on it as it is rather self-explanatory, but we'll get to that in a second. And then the second step of the website presentation that I'm going to show you here is a suite of time series analysis that I like to call hydrology. I'll get to the reason why it's called like that in a second, but I just wanted to give you a quick overview of what we're going to go through with our website tools. So the water budget tool is a distributed water balance model. Its function and its parameters are distributed in space based on superficial geology and land use mapping, and they are cross-referenced with lookup tables. Pretty basic, pretty simple means of doing a water balance that we've seen done all over the province. And really, in a very simplified way, I'm trying to I'm modeling this equation on a cell-by-cell basis. So we're looking at how storage in the system is changed based on precipitation inputs, based on losses due to evapotranspiration, due to runoff, and due to groundwater recharge. The water budget tool has the current version that's on the website that I'm going to demonstrate today is on a coarser resolution and a coarser model time step. The next version, which is soon to be released, it's on our horizon, has made improvements based on feedback we've had for the last couple of years with the current version of the water budget tool. The main reason also that I want to change or that I want to update the model is some of the requests of just having long-term annual average outputs and move that into something a bit more seasonal has come up a lot, and I agree. I'd like to see more seasonal aspects of the hydrologic regime within our jurisdiction. And most importantly, what we have online right now is just a single model realization. Think of that as your calibrated model, for instance. There's just only one result everywhere you click, everywhere you look for data. That's all that exists. Whereas in the next version, I would like to have, or I intend to have, a bounded ensemble, meaning sort of a low and a high ballpark for where some of these metrics may appear, may be reported. So just to give you a high level, for instance, the potential evaporation, and like every other model, there are submodels. So the potential evaporation model that I use is the McKink method, and I use this in coordination with solar radiation theory. I chose this because it isn't data intensive, yet it follows the structure of more common commendation type evaporation equations. And you can see this model calibrates quite well to certain observed pan evaporation stations. And so with that submodel, with the mapping and the cross-referencing and all the topography and what have you, you get this pixelated picture of long-term evaporation. And a lot of this is dependent on recharge rates, and a lot of it's dependent on storage capacity. In a similar fashion, once we have an idea of the runoff, and once we have an idea of this evaporation, once we have an idea of what type of percolation rates would be permitted by this official geology mapping, then we get this idea of recharge and how that relates to our jurisdiction. I am going to now move to the live demo, and hopefully I can make this work smoothly. But let me just get to my web page here. Okay, I think we're good here. So we've all seen this. Here's the home page. Here's the page you get when you log in. I click maps, and here's the maps that come up. So we'll just move to this consolidated mapping. Hopefully all my login info has been saved. Looks like it has. So once this opens up, it takes a little while to load. Course, there are disclaimer pages. I just wanted to make sure I go through all this, just make sure everyone is on the same page. And hopefully I don't have too many people on it at the moment, because I know that's been slowing things up in the past, but just bear with me here as we watch these loading bars go. So what we want to find here specifically is the water budget tool. And I'll just follow. Okay, here's my, I just need to accept that, of course. So now we own your cars. And so first thing I usually do is just turn this on to layers, but we want to look at the water budget tool. So there is a drop down here. And this drop down has what's called themes. And this is all the sort of types of maps that we have available to you. So I just move to the water budget here. This is where what's going to open is that single realization of the beta version of the model. And you can see it covers quite a big swath of our jurisdiction. And quite simply, what you can do here is you can, if for instance, there was, let's give a hypothetical, there's a, planned development within this block, right? So interesting tool you can do here is that there's this water balance button. Doesn't want to open now. 1 second. Yeah, I'll have to exercise patience. Of course, everything works before you do a presentation, and a live demonstration always tracks you down here. Okay, so here we go. What I'm going to do is I'm going to draw an area on the map. I hit that, continue. The other option is to upload a polygon, so with a shape file. I don't have one on hand right now, but you could say import a watershed and get the same idea. But I'm going to move with a drawing a polygon, and I'm going to select a polygon, and I can do something just quick and easy. If we just want to look at what's the overall water balance in this area, to finish the square, I double click on that last corner. It says geometry captured, hit continue, and this is going to crunch away, take that raster that exists within that polygon and spit out a water balance for this area. So it's a really quick and easy, quick and dirty way to get a sense as to what kind of hydrological setting that we have within that particular area. And you may be tempted to add these up. Sometimes they may not add, because remember, there is storage in the system. So some of the storage may be still within the soil zone or within a portion of the model. But hopefully it should zero off pretty quickly. And so there's recharge, and of course we have runoff, and just like I showed before, we had the change of storage equal precip minus evapotranspiration minus runoff minus recharge. So here we have that picture. And so it's pretty self-explanatory. You can poke around at a particular spot, and it will give you value of that current layer at that particular location, and yeah, you can go wild with that. So I'm just going to, or you're gonna have to bear with me here while I get my screen back in order here. And I want this one. Okay, back to the presentation. So that's the water budget tool in a nutshell. I do have documentation. You know, I'm not going to go through all the nitty-gritty details of the water budget tool, but it's there, and it's there to help give you an idea. It's not the definitive model of the area, but it's just there to, you know, really give you a sense as to, you know, what's going on in a particular area, in a particular zone, or whatever your area of interest is. Okay, so now I'm going to move to the time series analysis part of our website. And I told you I've called this hydrology, and it's a bit of a stylized term combining Shiny, which is an open source product, let's call it, and hydrology. So it's just a play on words. You see it for other Shiny projects, so I just sort of followed suit. And so as a hydrologist, I had a lot of workflows, like I was talking about earlier, workflows coded in a variety of languages. But for me, the limitation of those was that they were only available to me when I was sitting in front of my workstation. A couple of years ago, I was introduced to this idea of Shiny, and basically it just allowed me to take those workflows and put it out in the cloud, let's call it. We can hit on our database directly, and I can run these workflows from anywhere. I don't need to be at my station, and this is very powerful, because at times there are certain questions that may arise in a meeting, and I'll go through an example, but it's nice to be able to pull out a laptop in a meeting and just quickly look at a station, quickly look at the recent conditions, and quickly make an assessment to see if it could, you know, maybe it might help steer the meeting in a proper direction. Otherwise, we would have to sort of take note. It will be an action item. I'm going to go back to the office. I'm going to run my scripts. I'm going to produce the plot. And then maybe the next meeting we'll come back and we'll discuss what's actually going on there. So this is a means of efficiency. Like Rick said, we put our brains on the internet, and this is what we had. So all my scripted workflows were rewritten in R. R is a statistical package. It's free. It's open source. It's got a great user base. It's come a long way, even in the last 5-10 years, I would say. And having everything in R, the Shiny is just a wrapper. And basically it says, it takes your R scripts and says, let's put it on a website. And it's almost as easy as that. So there are 3 components to the hydrology suite of applications. The main one, the first one that I built, is called hydrology, and this one is mainly for streamflow analysis. Streamflow has a lot of time series analysis out there, so that one is the most rigorous. It has almost anything I could find that is useful to me, I put onto the hydrology suite of tools. ShyMet is a climate analysis tool. I'll go through that again. It's the same type of tools, but this one's more focused towards temperatures and precipitations, what have you. And then lately, I've been generalizing these packages into just Hydrograph. And in this sense, I'm using it more focused on groundwater monitoring. And we are slowly incorporating more ways to look at groundwater monitoring, more time series analysis processes, and I'll go through those in a second. But overall, every variant of the hydrology suite has been grouped into sort of 4 types of analysis. The first one being the raw data. Just looking at the data, looking at what's been queried out of the database. And this is great for quality control, because right off the bat, you can see if there's spurious data or if there's data gaps or what have you. With that, when we have long-term data, there's plotting tools to look at long-term trends. There's statistical tools to look at common statistical means of looking at the character of whatever time series you're looking at. And if we're lucky, if we have data that is up to date, there is a real-time data analysis bit to that. And that only appears if we do have an active station. Before going to the website and showing these and risking a live demo, I want to go over a couple static screenshots of the tools because I'm not sure how I'll be able to go over everything live. And so how I've structured this presentation is to go over some common questions that come across our desk and show how I can work through that using our website. So I've had a few other presentations in the past really explaining what my objective here, and there's a term out there called information content, and this is the information, well, it's written right there, contained within the data. So data exists, we have it in our database, but there's a lot of information that is outside of just the raw data that you may see here. So for instance, just looking at this Streamflow hydrograph, we can identify both major and minor events. We can get a sense of the seasonality and of the flow regime. We can also isolate the delayed signature, in this case, stream flow or base flow recession, pardon me. And capturing this information is a great example of where a workflow is needed and which have been automated onto our website. So probably one of the first tools that I put on this was hydrograph separation. And this is commonly used in the Hydro-G community. It's a good surrogate measure of recharge that occurred within the system. And fortunately, these are all automated scripts that I had written before, and I had put them into R, and now they're available on our website. So with that base flow, we can look at seasonality of base flow and how that affects and how that changes through the year and how that changes from recent to past. We have your standard peak flow analysis type tools that give you a sense as to what that 100-year rainfall event or what have you is. There's other bits of information here, such as the density of these peak flows and the months that these peak flows occurred. So in this case, we see a lot of spring freshet. That's where those peaks are happening. That's when those floods are occurring within the watershed. And this is all readily available on the website. There's an automated stream flow recession computation. And there's also this idea of high-low recurrence. So looking at what time of the year do we typically experience high water levels, and what time of the year do we typically experience low water levels? And this really helps for planning and helps for design and what have you. Just the one thing I want to say, that when we hit the database, none of these images are canned. The power of Shiny is that these get generated on the fly on your machine. The only thing we take is the raw data. That is just the temporal time series, and all these things get built into this. And this is where Shiny is fantastic. So moving on, I'm going to move to a live demo, and I'm going to spend a bit more time on the website here, but we're going to look at these hydrology tools. And like I said, I'm going to go through some common questions, common asks of us that I can hopefully demonstrate is accomplishable using our website. So just give me a quick second here. There it is. Okay, so now we're back to the website. So I'm just going to close out the screen again. Oh, maybe I should have kept that open. Let's go through. So here's an example of something that may come up in a meeting that would always be great to know right offhand, that up until, for me, up until getting this website available to us, has always been, okay, action item, I'll take it back to the office, I'll look at the data, and then I'll come back to you. So question could be, residents in my area are worried about some development nearby, their water levels are dropping, stream flow is dropping, and they think it may be the development, and that question often comes to us. And so we can have an example of, let's just say, let's take first the perspective of what has the climate been in the most recent times. So I'm going to just zoom in, let's just say in this Aurelia area. I'll let this load up here. Things are going a bit slow as usual, but so right now the default map you get is active climate stations. So these are stations that are, like they said, active, they're current, and they have recent data, so that's nice. So let's just say somewhere in this area we had, some issue of development, people's water levels are going down. I can click on that station, and the first link you see here, display meteorological analysis for cold water warm minister. Cold water warm minister is the station. This will bring you into the Shiny application, specifically the Shiny application designed for climate data. And like all stations, it always opens up first to this raw data scene. So this is the data that have been queried out of the database. That query just happened right there when I clicked the button, when I clicked the link, and this is the data you come with. And at times, this is all the data you need to make an assessment. But I'll just show you a couple clever little things that are worked into this. So if you just zoom in, just to forewarn you, this often can happen. You just have to hit this reload button. At times the server drops, and maybe it's because other people are on it, but I don't know. And all you gotta do is hit that reload, and it should reload. Oh, we're gonna do one of these today. That's a bummer. Of course, I'll tell you that all this has worked. I never do live demos for this very reason, but we have to do it since this is a presentation of our website. And this may hinder my presentation, but in any case, what I want to get to you is to show you that, when you zoom into these areas, and you can sort of move a little window here, if you notice down below, the values are changing. So the values basically reflect what's in this window right here. That's the select data range. And what's the entire data range. And the entire data range you can get by double clicking. So this is right off the bat, a quick way to just sort of see, what's going on recently. I can zoom into this area and say, what precipitation is about 100 millimeters a year higher than it has been for its history, and that's in the last 10 years. Right? Darn. So going back to the question, has development had an impact in this region? Oh boy. This is a bummer. What I'll probably have to do is re-record this live demo, and when we put it up online, yeah, I think this is going to be a problem. Maybe if everyone's there, if you could kindly not follow along, and we'll work through this. So the first one I'd go to this real-time point here. And so this real-time is a nice plot because it's going to show monthly precip levels. Precip is what's picked off here. Monthly precip levels, the most recent, June, May, April, going on back, and how that compares to average conditions, average Junes, average Mays, average Aprils. So in this area, if someone's saying, my well's gone dry, well, first off, I would look at this and say, well, you know what, it's been a relatively dry period as of late, so there are compounding effects. I could also look at another accumulation field. Good thing the queries aren't taking long. So this is another plot, and this was looking at your last month of data, and you can sort of see after, say, 7 days, there was probably a good 2-week period of zero rainfall, and that has, and so with the impact of no rain, of course you're going to expect drier conditions. We can also look at this from a groundwater level aspect. And so here there's a nice PGMN well right here, and there's a couple ways to look at the time. There's a time series analysis here. That's what we're going to go to. There's also another hydrograph tool. Steve showed that a couple weeks ago, but I'm going to go to time series analysis because that's what we're here for. And again, this is also going to open you up to a raw view. So this is the data we have in our database. Up top here, we have what's called atmospheric yield. I will explain that. Well, I explain it now. So at all these locations, remember we're talking about the interpolation between points, and some of that requires modeling. So the problem with our climate stations is that they collect snowfall and rainfall. And snowfall isn't really a good parameter from a groundwater perspective because that snow sits on the ground, it doesn't affect the groundwater system. When it does affect the groundwater system, of course, is when it melts. And you could see from many of these plots, you could see the response that occur right immediately after. So here's a major snow melt event and the groundwater levels rise, and so on and so on. So I'll speak a bit more of that modeling, but here, for the sake of our question, why are my wells going dry? We can also look at another trend analysis. Now, unfortunately, this PGMN well that we have only goes to 2015, but what it does show is that there is seen about a 6 to 8 month lag in water levels with respect to the spring freshet. So according to these data, we have seen drier or lower water levels in that April and that just prior to the winter season, whereas the water levels start to creep up in the June and July. So at this time of year, we should start to see that high water level rebounding. But if it had occurred in May, it might be still questionable. But just to say that historically, this groundwater level tends to be low at this time of year. So with groundwater levels being looked at and climate being looked at, recent climate being looked at, it might not be fair to conclude that the development has affected your water table. But this just gives you that little bit of insight, and should the website not have to reload all the time, you would have had that in 5 minutes. So that's kind of one example. Another example I have listed here is we're getting actually quite a bit recently is what is the range in water levels? And this is a pretty interesting question because quite recently a consulting partner of ours or of our program had asked to have implemented a means of looking at possible maxes and mins of a groundwater table. So I'm going to open, I opened the wrong one. For some reason, I do that all the time. So I'm going to open the shiny version of the hydrograph. This was the one that Steve showed earlier, but here's the shiny one, and it's taking some time to load again. But as always, you open up to the raw data. This is the data that's in our database. I like to turn off temperature here because temperature is relatively, in absolute terms, quite low. So as soon as you turn off temperature, it pops up into, you can see the data much better. So in this case, what we've added, we've sort of taken a page out of the hydrology peak flow recurrence book. And I'm just going to move this to the logger data. And this is, it's sort of taking a methodology from hydrology. It isn't really a consistent way of using peak flow analysis. And I've written so here, see, please use with caution. So please read everything that's that's below these tools when you're doing this. But for the sake of this presentation, we could use this as, let's call it back of the envelope calculation to say, what is a maximum water level that we should expect? And we can take this model, and there's a number of models that we could choose from, but here's the log Pearson 3 model, and if I pull this out to the 100-year return, it gives me a sense that 170 and a quarter meters is your high, maybe a high limit to your water levels. Likewise, I can flip this over to annual minimums and let this crunch away. And in the same fashion, I can look at the 100-year low, which is 169.75. So we're seeing under a meter, maybe a quarter, 3/4 of a meter of fluctuation, given the data we have in the model we use to project that. And so right off the bat, we can get a sense that question is, or so for instance, if we have our water table map, commonly it's asked, okay, we know that that's a static water level taking as an average over a long period of time. What is the expected variation of that? And here in this particular area up in Vaughan, I would say less than a meter, right? Quick and easy, it's all there, it's all at your fingertips. So I'm gonna give you one more example, and this is a bit closer to my heart. And we're talking about flow regime and how stream response is and how that's changed over time. I'm going to go to a different set of maps. This is a map I tend to use. Right now, it only shows stream flow and climate stations. Climate stations, you can turn it on and off here. But this is the same data set, same points that are coming in on our data on our GeoCortex, the other version of the mapping. But I like to use this one because it gives a bit more flexibility. For instance, I have a date range selector here. Basically, all the stations picked here are stations that have data between 1946 and 2020. But what's advantageous here is if I pull this up all the way to 2020, these are all the stations that are active, that have data up to the last month or so. Similarly, I can pull, to look at data with longer periods of record. I can filter based on the minimum length of data. And so let's just zoom in, and I'm actually going to pick a station here. It's near and dear to my heart. Taylor Creek is where I grew up. It's where I learned how to ride a bicycle. And so this is a station hosted by the TRCA. And when you click on a station, you get basic information. You get the hydrograph. You can do the same sort of zooming and moving around and what have you. You can download the data right from this page, or you can click Analyze. You can click it here or click the link here. And this is another way to get to the Shiny app. And so this is the original Shiny map. This is the one for Streamflow. And you can see it's a bit more detailed, a lot more functionality. But the same sort of thing is what I have is a viewport here that when I move, everything adjusts with this window. So I'm looking at everything from, yesterday, looks like, and back to 2017. And so you can see in the last 3 years, we have increased flows in January, increased flows in April compared to the entire data range. We also see from this flow duration curve that the low flows have increased in this last 3 years. So quite often, this is the only page I really need because I can just do a quick, right off the bat assessment of how everything's going. I'm not going to go to base flow separation. I spoke to it a bit before, but it actually is a slower process, and I've already kept you waiting, watching this thing load up and crunch up. But that one will show you the base flow separation, hydrograph separation in terms of the overall total hydrograph. But this one here is what I'm calling streamflow disaggregation, and basically the streamflow is separated into its components of rising limbs, falling limbs, and the base flow reception in the red, blue, and green. And this is pretty key for hydrologic modelers out there because at times you may have a parameter that is meant to dictate that rising limb. And so if you can isolate those portions of the hydrograph where that rising limb occurs and calibrate to that, then you're really focusing that parameter on the function it's meant to represent. What you'll also notice is that I have some bar plots coming from the top here, and these are called event yields. So here's a figure taken out of Reed, Johnson, and Firth back in '75. And the idea here is that you have a total hydrograph, right? And you can also, and if you had the hydrograph and say, let's take a recession curve from that first peak and let it go down here, that would be the hydrograph should this event had never occurred. So what you can do is the space within this represents the volume of the event that made that hydrograph happen. And so what that ends up doing is that for every event, every time we get a rising hydrograph, I can compute the volume of that storm and in a sense, discretize a continuous data set into what are called event yields. And this is also another important, it's also important for hydrologic modelers out there because they may want to look at those event yields and how does it compare to actual rainfall events. Right, because quite often you get rainfall events that occur, but the data density isn't all that well, so your stream flow doesn't respond, or vice versa. You may see a bump in your stream flow, but there was no climate forcing to get your model to do that. So those are areas where the calibration is going to lead you astray. So those are all interesting tools, and of course these tools can be downloaded after the calculation. So here you see falling limb, rising limb, what have you. If you hit the include all calculations, that gives you a whole bunch of stuff, and you can see the, this nomenclature here. But all you got to do is go to the about page. I've tried as best as I can to document that, and here's all the base flow separation procedures. So even if you don't like my tools, you can download them and do whatever you want within your own suite and workflow of preference. Just going to go for one more example here. And we're going to talk a little bit more about flow regime statistics. And I think I'm going to go, I'm going to go up here. This Rouge River is a good example. So Rouge River, I just selected something with greater than 50 years of data. So the longer the data, the better it is to do some of these analysis. And again, what this opens up is to that initial query. Here's the data set that we see. Same sort of tools and workflows apply if you want to see how things have changed, within a certain period versus the entire data set. It's all there. I forgot to mention there's a button here to say show observed data flags. So there's ice conditions. There's some estimated discharge here. So these are the quality flags that get associated with a lot of these measurements. And so if I want to ask a question, if I want to answer the question of how has the watershed changed in the past, how, do we see any signature of something occurring in the past that has affected the water or affected the flow regime, the quickest way to do that is through this cumulative discharge plot. Now this takes a little bit of time to compute. But what I want to show you here is that we have total flow here and base flow here. The dotted line is is the expected route. And so anything that's going down is meaning that it's been slower than expected. And at some point here, it picked up and met up with its expected value. And so the blue line that's superimposed here, that's a piecewise linear regression. Thank you, R. This isn't anything really sophisticated other than you can do outside of R. But it tells me that maybe something happened in 2008, which picked up the flow in the Rouge Valley up in Markham. A more detailed way to look at this, and this is 3 decades old now, means of looking at flow regime. It's the indicators of hydrologic alteration. Now, probably the drawback of this is that it involved a lot of computation and a lot of work. It was quite a tedious workflow. And fortunately, there is a package in R that does this for you. And all I've really done is present these into this web platform. So here we go. So I'm gonna just pose the question here. So let's look at, okay, something happened in 2008. I'm gonna double click here to get the full data set. I'm just gonna sort of picture an imaginary line, zoom that across here. I'm gonna pick an imaginary line, zoom that across here. So I have a selected data range from 1962 to 2004, and I have another data range from 2002 to today, right? And so what these tables are telling you is that are the mean values of these magnitude of monthly water conditions, all these groups. It's all listed down here. You know, you get your information here. But where it's red is indicative of a significant change in that parameter. So we know the magnitudes of monthly flows have increased in that last 10 years. We know that minimum flows, interestingly, have increased in the last so many years. And we know that high pulse length and the number of high pulses has, well, the lengths have decreased. It's gotten more flashy, but we've seen more of these flashy events. So again, quick and dirty way, you know, when we're looking at how has development affected a watershed after time, we can look at this and you have, I think, 32 metrics here to sort of pin down how things have changed. And the last things I'll just do with this sort of live example, and thank you everyone if you've stopped using it, because now it's moving quite smoothly. Oh, Steve's taking my screen here. Someone took my screen. Hold on, I'll go right back to it. Okay, we should be back. So this is just your standard peak flow analysis. You've seen this before, a couple slides. Again, you can see the distribution of these peak flows and the seasonal distribution. When did those peak flows occur? And from this, you can pull off what that 100-year flow is. You can choose a different model, what have you. It's all there for your liking. Quite often, I'm interested in low flow occurrences. So this is the same type of tool. Rather, we're looking at 1 and 7 and 30-day low flow occurrences. So for instance, if we are, well, once this all loads up, it's 3 plots that it's going to come up. But we can ask a question like, you know, if we see stream flow currently in Rouge River near Markham is 0.06 cubic meters per second, we can get a sense that, well, that's the 10th year recurrence of a low flow. And we see the same thing with, weekly totals and 30-day means, mean annual minimums. And again, you can see when do these occur, and of course, they're all occurring during the summertime. So there's a lot of ways to pick and tease and pull out of this information to get out of this data set. And I will, one more. How much time do we got left? 2:57. Okay, I got like 3 more slides. I am going to just get back to that. There we go. So live demo done successfully. So I just want to talk about the future, what I'm working on now. And there's been a lot of great products that have come out in the last 5 years that extend back maybe 20 years now of these what's called data assimilation systems, or these reanalysis products. And these are fantastic because basically all that interpolation stuff that I used to do in the past is being done and delivered by government agencies. So we see, for instance, this is a precipitation field that's nationwide. It's taking nearcast weather forecasts and looking at that and comparing it against radar data, ground truthing it with stations to paint a distributed picture of precipitation. And this is available 6 hour timescales from all the way back to 2002. So this is a lot of work that I do not have to do anymore, and I can start to import it to the system and give people within our jurisdiction access to this type of great information. And lastly, with the interpretation, also working on multivariate data interpolation. So this gives you, sometimes you may have low stream flow, but you may have average precipitation, or vice versa. The stream flow doesn't seem to be affected by the dry spell we've had. And so to get a better sense of what is a drought, or are we in a drought, it's always more sensible to incorporate all the bits of information, monitoring groundwater levels, stream flow, and climate stations to get a picture of whether or not we are in a drought or a wet period. And so this standardized index kind of comes about, and we're, for this example, we would be in sort of the wet period versus, a few years back, it would have been considered dry. So this is a good index of trying to determine droughts and what have you. And so with that, I thank you. 55 minutes is my timing here, and looks like we are good to go for questions. So I'm gonna give the mic back to Steve. And again, thank you all for listening to my presentation and being patient with our database.